Hi and welcome back to my channel. So today I received a new toy, the nanoVNA, and I'm pretty happy about it. So I paid around 50 euros, shipping included from Amazon, and shipping time was about 1 week. So it's a relatively low cost device. It is a vector network analyzer. So a vector network analyzer, you can probably read the Wikipedia page for an introduction, but for me it was extremely useful to just follow the lectures basically of some YouTubers, including W2AEW, fantastic. But also on the topic, especially the nanoVNA, there is also this channel which is very good, Joe Smith, and also this other channel is pretty interesting. So I suggest you have a look at this channel if you're interested about understanding what in general what a vector network analyzer is. So here I basically in this video I just want to give a very quick demonstration, and especially I want to verify if these things works properly, because I read online that some units are not so good, so I want to check if the readings of this vector analyzer are okay. So anyway, as you can see, the nanoVNA has two ports. These two ports are used to measure two different things. One thing is called S11 and the second thing is called S21. Okay, both things are complex numbers. So let me just remind you what a complex number is. It can be a bit scary because it's a bit a mathematical subject, but in fact in this context it is very simple. Well, here I am in just numbers, so let me search for complex number here. Yeah, so a complex number is not just a number, it is a vector on the Euclidean plane. Okay, so it is a vector, meaning that it's basically an arrow starting from the center, and it has some length. So this is called the magnitude of the complex number, and it has an angle with the vertical axis. Okay, this angle here, and that is called the argument or the angle of the complex number. Okay, so that's all you need to know about complex numbers. And the complex number that we are going to measure in this video, S11, well, it's composed of two things, right? The magnitude, the length of the vector, and the angle. So the magnitude is proportional, so the vector network analyzer emits a signal, and part of this signal will be reflected back by this unit. Okay, so if this was a perfect 50 ohm load, it would not reflect anything, but basically everything in real life reflects a little bit of the input signal. Okay, and the ratio between the input and the reflected signal, the ratio in power, that is the magnitude of the complex number S11. And then this reflect signal might also be out of phase compared to the input signal, and the difference in phase between the input and the reflection is going to be the angle of the complex number. So once again, the length here is going to be the ratio between the power of the input and the power of the reflection, and the angle here is going to be the phase difference between the input and the reflection. Okay, so in theory that's pretty simple. So let me zoom in here so I can show you some more details. At the moment, as you can see, I'm testing this unit. This is a low pass filter I made. It's about 10 megahertz low pass filter, and here the other end is terminated by a 50 ohm load. So this means that the signal that is entering from the nano and going to the filter, well, the idea is that the low frequencies are allowed to pass and reach the 50 ohm load. Instead, the high frequencies are going to be reflected back. And this is what we are seeing here in this graph. This is called the return loss graph, and it basically represents the magnitude of the complex number S11. Okay, so for example, we see that low frequencies, the reflection is very small. But if we go to high frequencies, the reflection is large, is as large as the input signal. So the top line there is the size of the input signal. Right, so this is just the magnitude. You know, this magnitude graph, this is called the return loss graph. Another way to represent it, it's completely the same, is in terms of FWR. So this is used more by ham radio operators. So as you can see, again, at low frequencies, the reflection is very low. At high frequencies, it's very high. Okay. Right, but then of course there is also the phase, as we were talking about. So that's the other component of the complex number S11, is the angle, and this angle is expressed here in degrees. Okay, so that's this graph here. Another way to see both things together is to look at the polar form. So yeah, basically when we in this graph we have plotted all the complex numbers. So these are vectors, basically. A point is basically the arrow from the center to that point. And the further away that point is, the greater the attenuation. And then the angle is just the angle in the plane. Okay. So anyway, this is what the nanoVNA is measuring, and I want to check if this is correct. Right, so to check this, I'm going to use both the spectrum analyzer and the oscilloscope and the signal generator, as I will now explain. And to remember what the measurements were, I took a photo of the nanoVNA. So let me zoom in again and show you the photo. So and this photo is basically, so let me go back here to logmax and back trace is this photo here. Okay, so we are seeing both so on the top the yellow line, the orange line, is the magnitude of S11. Instead, the green line depicts both the magnitude and the angle, so it's the whole complex information. Okay, so I just took that screenshot to remember what it was. And beside that, I also took some notes here. So let me see if I can show. Yes, over. Oh, sorry about that. So let me see if I can fix. I hope. So yeah, let me place the information I had here. And as you can see, I took the precise information of S11. So both the magnitude and the angle at 4.046 megahertz, 13 and almost a half megahertz, and 15 megahertz. So I'm going to verify if these values are correct. So in the next, in the rest of this video, I will check these values. Okay, so I'm going to use first the spectrum analyzer to verify if the return loss curve was correct. So the spectrum analyzer, my spectrum analyzer, which is the HP8591E, has a tracking generator. So spectrum analyzers with tracking generator are often called scalar vector analyzers, okay? So they can do basically the same thing, I mean the same type of measurement of the nanoVNA, but they can only measure the magnitude, so not the angle of the S11 here. So basically the setup that I have here is the tracking generator is going to emit a signal. Let me actually activate the screen of the spectrum analyzer so you can follow. So the tracking generator is going to emit a signal from 50 kilohertz to 50 megahertz. So this was the same setting we had here. I don't know if you can let me see if we can focus. Anyway, this was the setting we had on the nanoVNA. And now the signal is reaching this point, and then it will be connected. So the signal from the tracking generator is reaching point. It will enter the unit under consideration, in this case the low pass filter, and some of the input signal will be reflected. This reflection is going to be captured and sent to the input of the spectrum analyzer. Okay, this reflection capture here is attenuated by minus 20 dB, so we will have to take this into consideration. So okay, I'm going now to let me see the tracking generator. Okay, So let me activate now the tracking generator. The tracking generator is going to output basically a signal at minus 10 dBm. As you can see here, that's the setting. And we are going to get out the reflection. For the moment, I'm not connecting the unit, so everything will be reflected back. And the reflection will go attenuated by minus 20 dB here. So let me just run it so you can see what's going on. We are getting this line as minus 30 dBm. That's natural because the signal was at the input signal was at minus 20, and we are getting back a full reflection. So also, sorry, the input signal was at minus 10, is at minus 10. And there is nothing here, so we are getting a 100% reflection, and the reflection we are looking at there is attenuated by minus 20 dB. So really this reflection here, this flat line represents a 100% reflection. So I'm going to actually normalize this response so that we see a 100% reflection is going to be just the flat line above, okay? So let me connect now the low pass filter so we see what is the response. And as you can see, is pretty much the same response that we had here. Is this same type of curve as you can see here. Right, so the peak that we had here, the lowest peak that we had in the nanoVNA was at 4 megahertz and something. So let's see if the same thing holds here. Yes. The second peak was at 13.5, and that's the case also here, as you can see. And yeah, so everything, the shape is correct, and the frequency information is okay. So let me see also the data. At 13.5 we measure minus 12, and on the spectrum analyzer we're measuring minus 13, so that's great. At 4.0 here we measured on the nanoVNA minus 17 dB, and here we are measuring also minus 17 dB, which is perfect. And at 15 basically where is it, here we measure minus 4.41, and the same measurement is valid here on the spectrum analyzer. So for what concerns the magnitude, the nanoVNA did a perfect test, exactly as good as the one I can do with my spectrum analyzer. So now I'm going to verify the phase information, which is the reason I bought this unit. This is because the spectrum analyzer, once again, cannot measure the phase information. Only a vector network analyzer can. Okay, so for measuring now the phase information, so the angle of the complex value S11, I'm not going to use anymore the spectrum analyzer, so I turn it off. I'm going to instead use a combination of the signal generator and my oscilloscope. This is just a very simple analog oscilloscope with 20 megahertz of bandwidth, but it will suffice to do some basic measurement. So the idea is the following. With this signal generator has two outputs. One of the these two outputs are going to output the same frequency with the same power. Okay, one output is going to channel 1 of the oscilloscope. Okay, so if I activate this output here, we get the signal. Okay, the same identical signal is going to the coupler again. The coupler will then, the signal will enter the low pass filter, and once again, just as before, the reflection will go through this cable to channel 2 of my oscilloscope. Okay, so at the moment there is nothing connected to the coupler, so I expect a 100% reflection going into here. And so let's see if that's the case. I'm going to evade this yellow output, and that's it. Indeed, as you can see, I get in channel 2, which is this channel, a reflection which is as big as channel 1. I actually cheated a little bit, so I already set up the scale of the two channels to compensate for this minus 20 dB attenuation that the coupler has for the reflection. Okay, anyway, now we can see that we have both the input and the reflected signal, but the two are not, they have the same magnitude, the same amplitude, but they are out of sync, okay? They are out of phase. So to compensate for that, I'm going to change the phase of the signal going here. Instead, the signal going here is not going to change the phase. By the way, the phase difference is due to the fact that one signal, this one, going to channel 1, is going through this cable. Instead, the channel 2 is going through the white cable, is reflecting, entering this cable, and going there, okay? So the difference in length is causing this difference in phase. So let me start tweaking the phase, and the idea is to tweak the phase until the two signals are basically one over the other. So let me see if I can be as precise as possible. So here it looks like they are perfectly overlapping, okay? Now I'm measuring here 170 degrees. So let's remember this number. Okay, now I'm going to connect the low pass filter, so we see what is the difference in response. Okay. Yeah, so what I did just before, so let me backtrack a second so I'm clear about this. By setting the phase of this input to 170 degrees compared to the other, I'm basically normalizing the two signals, okay? So I'm compensating for the difference in length of the two cables. So basically this operation was just to compensate for the difference in length. So now let me connect the low pass filter once again. Okay, so now as you can see, we still have our input signal, but the reflection signal is much attenuated, and so perhaps we can have a look at the data we had. So let me put it, I don't know, there. So the attenuation was at this frequency minus 17 dB. So let's see if we can also obtain these results just using the oscilloscope. So I have to basically, so let me see. The input signal is exactly 5 division, the amplitude is exactly 5 divisions. Instead, the reflection signal is 0.8 divisions, I would say, yeah, more or less. So this is going to be a more or less measurement, but that's enough. So let me go here. So we have our input. So this website, by the way, is a simple website to do basic calculations. It's pretty nice. So our input signal is 5 division big, and the reflection is only 0.8 division big. So the ratio is of 0.16, okay? So 16% of the original signal is reflected back. If we want to express this in terms of power, in dB, we have to apply the logarithm in base 10 of this ratio, and let's see if I can close this parenthesis, and then multiply by 20. So that's the standard expression that we have. And so the value that you extract from this is basically 16, which is essentially very close to the minus 17 that we measured both with the nanoVNA and the spectrum analyzer, okay? So that's not too bad, considering that you know, we just measure things very roughly in terms of divisions. Okay, now when it comes to measuring the phase difference, let's see what we can do here. Right, so let me increase as much as possible the reflected signal. This is the maximum resolution of this scope, and I basically want now to tweak the phase again of my input signal to overlap with the reflected signal. Now we are at 170 degrees, okay? So that's the starting point. And so let me move around, okay? So I'm okay. So here it looks like it's pretty correct. I would say that this is kind of what we wanted. So let me reduce a little bit the amplitude here so we can, so it's better. Okay, so I would say now I'm measuring, yeah, that looks precise enough to me, 46 degrees. So if we do the calculation, we have 170, which was the starting point, minus 48, which is what, 46, which is what I'm measuring now. Yeah, that's 124, whereas the nanoVNA measure 113. So I think this is pretty good. Oh, sorry, this is the wrong frequency. So let me see what I just observed. That I've set up things with the wrong frequency. So let me redo the experiment here in terms of the right frequency. So let me see, channel 1. Frequency, I have to specify 4.046 megahertz. Okay, and so as you can see, the amplitude basically is the same, but the phase has changed a little bit. So let me switch back to channel 2 and play a little bit with the phase again. So okay, now I measure 53. So 170 minus 53, well, I'm measuring now 117, which is really close to the 113 degrees that we measure with the nanoVNA. So yeah, the measurements are spot on, and it's really unbelievable that this very cheap device can be so precise. And by the way, we only talked in this video about the S11 complex value, but there is also the S21 complex value, which is also very interesting. Maybe I will talk about this in another video. Anyway, if you have any questions or any suggestions for what to do with this device, please let me know. The application I have in mind is once you have the S11 with both the magnitude and the angle, you can precisely characterize the complex impedance of the low-pass filter or other devices. So that's why I was interested in buying this thing. Okay, that's all for this video. See you next time. Bye bye.